go on page 621, they have two proofs here. Both of these are on your formula sheet. And anything that is on your formula sheet, you are allowed to use in a proof. Okay? But for now, before we just use this, like if you saw a secant squared theta in a proof, you could immediately change it to tan squared theta plus 1. Or if you had a tan squared theta plus 1, you could immediately change it to a secant squared theta. So anything that's on your formula sheet, you can use directly in a proof. Well, we're going to see where this proof comes from using our old strategies. So far, I've only taught you basically two main strategies. Strategy number one is any trig function can be changed to either sine or cosine or both. If you can do that, start with that. So secant squared, I can change to 1 over cos squared. And tan squared, since tan is sine over cos, tan squared will be sine squared theta over cos squared theta. So to start, I start with my main strategy, change everything to sine and cosine. Then, second main strategy is, if possible, write both sides as a single fraction. My right-hand side is already a single fraction. My left-hand side is not. It's adding. How do I add fractions? I would need to get a common denominator. So this 1, I would have to multiply by cos squared theta over cos squared theta. And now I would have a common denominator of cos squared theta. And on the top, I would have sine squared theta plus cos squared theta. So in our previous examples, almost always, when you did the two main strategies of changing things to sine and cosine and getting a single fraction on both sides, once you did that, almost always they were done. But this time we're not done. On this side, we have 1 over cos squared theta, but on this side, we have sine squared theta plus cos squared theta over cos squared theta. Do you see that your denominators are the same? The only thing we have to do is somehow figure out how to get our numerators the same. Do you recognize the big idea on the top? Sine squared theta plus cos squared theta is one of our big ideas from chapter 6. That's always equal to 1. It's on your formula sheet. You are allowed to just change it to 1, no problem. And then our proof is done. But you'll never be asked to prove this one again because it's on your formula sheet. And so is the other one that's listed there. That 1 plus cotangent squared is equal to cosecant squared. Highly recommend that you have all of your formulas for identities memorized, and you use your formula sheet as a double check. If you're like, ooh, am I sure that it's that? Is it 1 minus tan squared equals secant squared, or 1 plus tan squared? Then you have your formula sheet to check. Second reason it's important to memorize them is for those of you taking AP Calculus next year, you have to have all of your formulas memorized. AP Calculus has no formula sheet. They give you a booklet of like, here are 5 pages of formulas that you should probably know for your exam, but you don't get them on your exam. So to start memorizing formulas already is very helpful for next year as well. So these are our Pythagorean identities. The big idea from chapter 6, sine squared theta plus cos squared theta is equal to 1. We just proved that tan squared theta plus 1 equals secant squared theta. And that 1 plus cotangent squared theta equals cosecant squared theta is the third one. In fact, if you know the first one, you know the other ones. For example, if I took the first one, and I took everything in the first one and divided it by cos squared theta. If that divided by cos squared theta this divided by cos squared theta, and this divided by cos squared theta, can you see that you have the second one? Because sine squared theta over cos squared theta is tan squared theta. Cos squared theta over cos squared theta is 1. And 1 over cos squared theta is secant squared theta. And you could do the same thing by dividing everything by sine squared theta and get the third one. So if you know the first one by memory, you can derive the other two quite easily. Next thing, for anything on your formula sheet, okay? Sometimes when we're doing proofs, students ask, how much work do I have to show? Because a proof will always work out. And I have seen, like we're gonna do these identities right here in a bit, okay? Can you do this? So I'm gonna just erase this second one temporarily, okay? I've seen students do this. I don't know what I'm doing, but I know they're supposed to equal. Is this enough work? Can I get full marks? No. What did I do? I just rewrote the other side on the left side and like, I'm done. They're the same. Okay? That is not allowed. You have to show some work. But there are some things that you don't have to show. And I guess a basic rule is you're allowed to do one thing with mental math in your head. But if you do two things of mental math in your head and do a switch and a proof, I have to deduct a half mark for not showing your work. Hi, Jackie.
I didn't want to disturb.
You did.
I did. Should I come back? Or is it like, you already blew it up now. Just ask me.
So what that means is that if in a proof you have a cos squared theta in a proof, can you get cos squared theta in this equation by itself using one mental math strategy? Yes. One mental math strategy says, I could get cos squared theta by itself by subtracting the sine squared theta to the other side. So in a proof, you are allowed, if you see a cos squared theta, to change it to 1 minus sine squared theta. That would be allowed, no deduction. You're allowed to change, right, if you have a tan squared theta in a question. You could change it to sine squared theta over cos squared theta, but I would be allowed to because it's one mental math strategy to move the 1 over to get tan squared theta by itself and get secant squared theta minus 1. I would not be allowed to, if I had negative cotangent squared, do the following. Okay? Can you see that you could get a negative cotangent squared theta by itself by moving the cotangent squared theta to this side and moving the cosecant squared to this side? So if you wrote 1 minus cosecant squared theta, that is not wrong. That is true. But that would come at a deduction of 0.5 marks because that's two mental math strategies in your head that happened. And not enough work was shown. So what would you have to do instead? You would have to take an extra step and say, I can get cotangent squared theta by itself by moving the 1 over. So I could just change the cotangent squared to cosecant squared theta minus 1. And now I can distribute my negative. This would be enough work. So in a proof, if you can do something with one mental math strategy, it's allowed. If you do 2 or more mental math strategies, then you get deductions. So you're like, if you're stuck in a proof and just be like, ooh, maybe Mr. GR won't notice, I'll just write the final answer on this side and pretend it worked. That actually loses you more marks than just stopping when you're stuck. Making up stuff loses more marks. Trying to make it disguised like it works will lose you more marks than just stopping when you're stuck. So, with that in mind, let's go to our first example. There we go. It says prove. So the first thing we do in a proof is we rewrite the question and we draw the line. I have cotangent and tangent, cosecant and secant. And so I actually might start on the left-hand side and say, maybe this is a good idea to change everything to tangent. But unfortunately, on the right-hand side, we can't change things to tangent. So I'm going to go back to our very first strategy. You can always change things to sine theta and cos theta. So I can change cotangent to cos theta over sine theta, and I can change tangent to sine theta over cos theta, and cosecant to 1 over sine theta, and secant to 1 over cos theta. Next, once you've changed everything to sine theta and cos theta, you want to get a single fraction on both sides. So obviously on the right-hand side, I can just multiply those together, and I have a single fraction. But on the left-hand side, I'm adding fractions, and I don't have a common denominator. Okay? So how do we get a common denominator? I would need to multiply this one by cos theta and this one by sine theta on both the top and the bottom. Okay? Number one error in proofs that gets taken off is an E3 error. Do you want to see what an E3 error looks like? It looks like this. And now I would have that common denominator of sine theta cos theta. And here I'm going to have cos squared theta and sine times sine, sine squared theta. Where was my E3 error? You can never write sine without a theta. If you forget a theta even once in a proof somewhere, even off to the side, if you're like just trying to give yourself a memory, oh yeah, I remember that tan is sine over cos. E3 error right there. Off to the side, far corner of your paper. The examiner would be like, oh, look at that. They forgot thetas, E3 error, right? Even if you like, you try to make it super tiny and hide it in the corner, they'll see it. And they'll take off an E3 error. And you're like, hey, oh, wait a minute up there. Looks like some thetas are missing. Let's just, each examiner has a microscope that's given to them. They look in the microscope, they zoom in, and sure enough, we're missing these thetas. So it's very important that you don't forget thetas anywhere all the way through. Okay. Now, we've got a single fraction on both sides. Usually you're done at this point, but now that we've learned some new identities, can you see that we have sine squared plus cos squared on the top here? That's our big idea. That's on our formula sheet. You can change that to 1. And now the left side and the right side are identical. And we are done our proof. So working with fractions, knowing all of your fraction rules, multiplying, adding, subtracting, dividing, super important for your proofs. They're like little puzzles that you have to make the left side and the right side the same. So let's look at part 2. for part B here. And first of all, I'm going to tell you that if you change everything to sine and cosine, it is possible to do this proof. It works out quite nicely and only takes about a page of work. But sometimes we can use other strategies to make our proof faster. And that's where it's important to have all of these formulas memorized so that you can recognize when a shortcut is available in a proof. So first of all, I see this proof and I analyze it a little bit before I get started. You don't necessarily want to right away just see, oh, I know I can change cotangent theta to cos theta over sine theta, so I'll just do that right away. Sometimes you want to take a look, analyze it a little bit, come up with some different ideas, and sometimes a strategy that you try doesn't work. And you might have to throw it away and say, I'm going to start with a new strategy. But in analyzing this one, I noticed that I have cotangent on this side, and I have cotangent and cosecant on the other side. And I know from my formulas, there's a relationship between cotangent squared theta plus 1 and cosecant squared theta. Which lets me, if I have, which I do on the right-hand side, I have a cosecant squared theta. Because it's on my formula sheet, I can change that to cotangent squared theta plus 1. And what's really nice now is both sides have only cotangent. So chances are I'll be able to get them to be the same. Well, how do I do with the number out in front? I would have to distribute, right? So cotangent times cotangent squared will give me cotangent cubed plus cotangent theta minus cotangent theta. These are like terms that will simplify, and we're just left with cotangent cubed theta and our proof is done. And I'm going to add a part C to this question. So you can add this one at the bottom of page, on page 623 or on 622 if you need more space. It's a proof, so we'll draw a line at the equal sign. And what makes this one difficult, well, if you change things to sine and cosine, again, it's possible, but it's going to be very difficult and very long. There is a shortcut, and we notice that we have tan squared theta and secant squared theta in this question. So we might think this is a good one to use our identities. Okay? Another strategy that's going to come up a fair bit in proofs is you have to be able to recognize when you have a difference of squares and can factor. So a quick reminder, grade 10 math. This is a difference of squares. Do you remember that? And you can factor this to be x plus 3, x minus 3. Two conjugates. Conjugates, again, one is plus, one is minus, but the numbers are the same. That strategy comes up a ton in proofs, and we actually have a difference of squares on the left-hand side. We have tan to the 4 theta minus secant to the 4 theta. Is this a perfect square? It is. It's tan squared times tan squared. Is this a perfect square? It is. It's secant squared theta times secant squared theta. Do we have a difference, a minus in between? We do. So we are going to start by factoring tan squared theta plus secant squared theta and tan squared theta minus secant squared theta. And of these two, one of those two matches up with this formula with some mental math manipulations. Can you get tan squared theta plus secant squared theta alone on one side of that equation? Or can you get tan squared theta minus secant squared theta alone on one side of the equation? Which one matches up with this formula? So you're asking yourself, if I took that formula and I rearranged things, could I get tan squared theta plus secant squared theta alone on one side? Or can I get tan squared theta minus secant squared theta alone on one side? Only one works. Close. The second. Right? Because if I move the secant squared theta to the left, it would be minus something. And then I have to move the 1 over, which is actually two mental math manipulations. So I'm going to start tan squared theta plus secant squared theta. And on this one, I'm going to substitute secant squared theta is tan squared theta plus 1. It's important that you do it in this question and not the first one, because only the second one is a rearrangement of the first one. Now, if I simplify inside here, do you see that you'll have tan squared minus tan squared, which will cancel out? And this minus sign will get distributed, and all you'll have left in this is a minus 1. And multiplying this minus 1 through, we get negative tan squared theta minus secant squared theta, which is exactly what we had. Perfect timing. And our proof is done. So, circle question 3, 5,
Cadence Morris and Sophie Cabral to the office.
6,
Cadence Morris and
seven,
Sophie Cabral to the office.
and 9.